All right, so I've seen a lot of people here. This is actually, we got a lot more responses to this event than we were initially expecting. So I'm kind of curious about which faculties everyone's from. So how many people here are in engineering, maybe in software a little bit? Or probably the majority. How many are in comp sci? Okay, yeah, solid, 23%. And how many are doing something else? Econ, business, this group. Oh, we got a couple of hands. Okay, all right, we've got a good mix of people here. So welcome all. This is DSC Machine Learning Workshop. So the goal for today is we're going to be focusing largely concept heavy on what machine learning is, what some of the things to look out for are, and how it applies to the real world. We will be running through some code, but you won't have to write much, if any, if you don't want to. So the motto is concept heavy, code light. So anyway, introductions. I'm Joe. Hello. I'm a DSC executive team member. I've kind of been fiddling around with machine learning for 6 months or so I'm a bit of a novice myself. But in the event that you guys have any questions that go over my head, we have the University of Auckland's resident machine learning expert, Reza here, who's left. That's it.
Too much pressure, guys.
So he's here to answer any of your really hard questions, so feel free to smash them up and give him some nice difficult ones. But anyway, so we're going to get on the way. So, my presentation's not working. There we go. So first we're going to talk about what machine learning and neural networks actually are. They're buzzwords we hear a lot, but a lot of people don't actually understand what they are. So neural networks and machine learning are a subset of AI. Now, AI can take many forms. For those of you here who play games, regular game AI, which sometimes can make great decisions and beat you, or more commonly makes very poor decisions. And it makes the game very not fun to play. But that's a hard-coded AI. It has set responses. You can often exploit those actions by playing to their weaknesses. You know how they're going to react when you do this action, and so you can push them to bad situations. But there's a lot of examples of AI that you might not see. The cruise control in your car is a very simple form, if-then version of a control. It's an AI, it's an intelligence. It's very basic, it's very dumb. It can't do anything outside of drive the speed and brake if you're going to hit something, but it is technically an AI. Neural networks are an emerging form of AI with the increase in computing power. They try to replicate something more organic, more human-like, something that can adapt to advanced data where we have unexpected, unstructured data. We've got images and we want to figure out, hey, let's identify cats from dogs. Let's figure out handwritten digits, all that sort of stuff. And that's what we're working on today, neural networks. So as designers of neural networks, we need to talk about what our roles when it comes to building a neural network are. So there's three main characteristics of a neural network. There's three main stages, I suppose, to building one. So we need to collect and train data, or collect training data, sorry. We need to design our neural network and then train it and evaluate the results and see how it works. And then we need to use the predictions. So in this case, it might be recommending like on a Spotify algorithm, recommending what next song to play, or YouTube next video, or Amazon what item you should next buy. And that's the final step, so that we actually like. But in every stage of developing a neural network, we are influenced by the human condition yet still. And this is actually a really big problem for these large tech companies who need to build these networks that are fair. They need to build an algorithm, like YouTube needs to build an algorithm that can fairly recommend videos that doesn't have biases. But every stage of this process can be impacted by our own fallacies and our own biases. So in the event of choosing a data source, I'm going to pick on YouTube a bit here. We will develop a student code, so I'm allowed to. In the data sources, YouTube's algorithm for blocking videos, they have a neural network they've designed which tries to block what they view as harmful content and demonetize it, so advertisers do not get put onto videos that are potentially harmful or dangerous or not great, put it that way, not safe for work. But so YouTube went, they clicked a whole bunch of videos that were definitely not good. We've had human people watch these, we've decided they're not suitable for advertisers, we've decided these are unsafe, not good for children. And they shoved all that data into their algorithm, and the algorithm learned, okay, this is what's not acceptable, and then it just started blocking and demonetizing videos. Seems simple enough, but there was a bias in the initial data collection, this first stage we've done here. The bias was LGBT channels. Some of you might have seen this. These channels tend to talk a lot about sex. That's the nature of their content. It might not be necessarily necessary for work or not appropriate. The advertiser might be perfectly fine. But the algorithm learned that if a channel was LGBT, regardless of what content they were making, they are not suitable for advertisers. Let's block them. And this was a big problem because some have this marginalized group that YouTube is unintentionally hiding. They're pushing to the bottom results and not showing them anymore. And that's horrifying. That's awful. If you're a YouTube studio, you're like, oh shit, that's not good. We're not good here. We've got to fix this because that's a PR disaster. When you're looking at it. And let's go to the next stage. Surely evaluation materials are one of the best neural network, but YouTube is my example of the day, sorry. But in YouTube's case, they have algorithms to recommend videos, and how do they decide what the goal of this algorithm should be? They've used several different metrics in the past. One of the first ones was watch time. So the algorithm tried to increase the amount of time people spend on the platform. It makes sense for Google, it makes sense for YouTube. They want to increase watch on the platform because they can show more ads if you spend more time watching. So if the algorithm tries to get you to watch longer, they are more profitable. But it has a downside of creators who made short videos, say high effort animation videos or cooking or any of this sort of thing, which takes more tech videos with design robotics and programming. These take more time to produce this content. It takes more effort, and you can't put out as many videos and they're often over a short length. So what we saw is the rise of these stars, so PewDiePie, Markiplier, Jacksepticeye, just name a few, of these creators playing games who could output 3 to 4 45-minute videos every single day, day after day after day, year after year after year. And the algorithm loved that because they went, oh, okay, these creators are great. They're increasing watch time. People will watch 3 or 4 of the videos and they make them every day. That's amazing. But you had these creators who got pushed off to the side and could no longer make money on the platform that algorithm wasn't recommending them. And so after Apocalypse, YouTube altered their algorithm. They switched from watch time to engagement. What's engagement? Well, it's likes, shares, comments, that sort of things. Again, dislikes also counts as engagement. If someone clicks a link onto your video and it brings you to the YouTube platform, that's good. The algorithm loves that. If someone watches your video and then leave YouTube, that's really bad. The algorithm doesn't like that. So that seems all well and good. Let's get people engaged on the platform, that's good. But what it led to an unintended consequence is a massive rise in extremism and misinformation, because the content that people interact with, the content that people find most engaging is the awful stuff, not just good. It's the stuff where, there's extremist right political. It's if you look up a video on running, let's push you to ultra marathon running, because that's more extreme, you get more engagement there. Let's show you recommendations for whatever you're looking at, show you something more extreme. It's create outrage, and we're seeing one of the biggest rises in misinformation in history right now in the 21st century due to algorithms like this that prioritize engagement and are prioritizing content which may not be true, such as vaccines or autism or something else. Flat Earth, moon landings, ringing bells. So as designers, if we make a mistake in one of these steps, we pick bad data with biases, we have bad evaluation metrics, we're going to end up with results that affect us negatively. It's going to hurt us, because regardless of what the results are, regardless of how we choose our data, we're going to be impacted. And so when it comes to designing neural networks, if you go listen to a career, obviously it's very early, this is an introduction workshop, you have to be aware that your code has consequences. What the algorithm you design and how you implement them and the stuff you may or may not foresee can come back to bite you. Anyway, with that, let's get started. So we've talked a little briefly about deep learning. So it's a deep learning is a subset of machine learning, which is a subset of AI, as I said. It works best on unstructured data. So that's Now, categorical data, like ticking a box, there's only 3 options. Which day of the week we do this in. Categorical data, that's structured data. Unstructured data is images, text, sound, stuff that's difficult to identify. Machine learning is very, very good at dealing with that sort of data. So for those of you who've got their laptops open, please go to this link now. We're going to be running through our example on there. Good to meet you on the table. Thanks, Zoom. All right. How's everyone getting on? We just about to cover them? All right. We're going to move on now. So, thank you. So when we're developing neural networks, we want to use something to make it easier, right? There's a lot of very complicated math that goes into behind these. We're not going to be diving into this math today, but I definitely encourage you, if you like math, to dive into backpropagation and all this complicated stuff. So Google has written an application called TensorFlow. It was open sourced in 2015 and is now run by more than 2,000 contributors worldwide. It's written in C++ in the backend, but it has handles in JavaScript and Python. And it's got JavaScript handles. So for those of you who enjoy working on web pages, JavaScript and HTML, you can actually write machine learning directly into web pages if you really want to. But TensorFlow is designed for, let's say, quick prototyping. It's very good for developing a quick model to get things sorted, but it has advanced features that allow you to optimize that model down to your use case once you understand how to. So the first thing we do is actually import the data set. So I'm going to tab over here. There we go. Oh, so this is Colab. This is another product built by Google. Shocker, Google Development Club again. This is basically allows you to run code in your browser. So to run a code block, just hit a little play sign here. It thinks for a minute, and it actually runs it. There you go. So that code is running on my browser. Now, something important to note about Colab, even though these code blocks are separate, it's all viewed as one big program. It's one big environment. So if you create a variable here, so we're importing TensorFlow, you can still access that variable down below. It's one big environment. So you don't have to worry about these code blocks being split up. So we're going to import a library called Keras. Keras is just an API built on top of TensorFlow that makes prototyping even faster and particularly beginner friendly. So today we're going to be doing, effectively for those of you who are we're doing the whole world of machine learning neural networks. And that's called the minced dataset. And the minced dataset is 70,000 handwritten digits. So we can just download that here. Let's just grab that. Or it's thinking. Don't you guys around that one? There we go. Okay. So we download the data set. We can actually look at the shape of the data. So we see we've got 60,000 images in our testing data and 10,000 images in our testing data and 60,000 images in our training data. Each image is 28 by 28 pixels in size. And we can actually see what some of the labels on the data is here by running this. So they're just random numbers from 0 and 9. There's the first 6, well, first 3, last 3. But anyway, we're going to go back to our slides now. So we're using the minced data set. Now, these guys have basically done us a massive solid, effectively. Collecting data is one of the hardest parts of machine learning. If you imagine, there's a reason why Google and Facebook and most big corporations scrape all the data they can as fast as they can and never let it go. Collecting data is hard. You need a lot of data to train a good neural network. So we've been handed on a silver platter for free 70,000 images because someone has gone out, got a couple thousand people to write and a few digits each. They've manually labeled what the digits are meant to be. They've scanned them with the computer and uploaded them to this data set. for us. So imagine if you had to do that yourself manually, you're one man, go and write 70,000 digits and label them for meters. It's going to take you a minute. So we're just going to work with this today to make our life a little easier. So in this case, we could give them the data sources. So we're going to create a neural network, but a neural network, as the name implies, is made up of neurons. And what is a neuron? Obviously, it's a biological thing, but in the mathematical sense, in a neural network, what is a neuron? So a neural network is effectively a linear function. It's a little complicated to explain, but it's effectively that. So we get given a bunch of inputs that go into our neuron, like this. So these are our inputs. Each input gets multiplied by another number. We call that a weight. They get added together in here. We often add a little bit extra, like a bias. It's got a bias, so it might be a number, basically. And then we pass it through our activation function, and it comes out the output. It's a very simplified sort of explanation, but we'll just do a quick little thing here. So say you've got, this is, so you get x0 multiplied by theta 0 plus x1, theta 1, so on. Add all that together, add the bias, label as b. And that's basically what the neuron is. It's really simple. Now, those of you who are quite into mathematics might notice that's really easy to convert with really easy to do with matrices, and they use a lot in neural networks. So if you're good at matrices and you love them, this might be a good career for you. But yeah. So the final thing we do there is we pass it through the G there, which is an activation function. And activation functions can come in many different forms. We're only going to focus on 3 today, which is sigmoid, which basically squishes, say the output is a 3000. We want to squish that down to a value between 0 and 1. It makes the neural network a little more friendly to deal with. It makes it train better, basically. There's also the ReLU activation function, which basically means if the value is less than 0 at some point, it returns 0. If it's above that, it returns the number. So if we have 5, it returns 5. If we have a negative 1, it returns 0. If we have 1,000, it returns 0. 1,000, it returns 1,000. So what does it actually look like in code? It's my control there. In code, we want to take our lovely image, 28 by 28 pixels, and we want to unravel that image. Imagine like rolling out a tape. You've got a big ball of pixels, you're going to roll it out into a big flat line. So if you imagine you've got a 4x4 grid of pixels, we take the top row, put them down here, and end up with a nice thing like that in one big line. And then we can take that data. In this case, we've got 28 by 28, so I think 784 pixels in that little image. And you do what's called a dense layer. So that's actually the first thing for a neural network, is this. That is a layer of a neural network. So you will come to learn neural networks are built out of layers. So we've built what's called a dense neural network, which means every single one of these dots is attached to every single one of the input images. Each one of these little neurons has 784 input lines going to it from all of the pixels. It's a lot. Very quickly, each one of those has got its own weight, its own, whole thing. A lot of variables very fast. We have, and last thing to mention really quickly before we move on is, so we've got 10 of them. If some of you who realize this is handwritten character definition, yeah, handwritten character, what's the word? Basically, we're trying to figure out which character belongs in which thing. So we've got 10 neurons, 0 through 9, 1 for each character, more or less. We're trying to figure out which one is which. And softmax activation, this is the final one we'll be talking about really quickly. Activation function basically means that all of the output values on the final line of the neurons adds to 1. So 1 would be 0.1, 1 might be 0.2, 1 would be 0, and they all add to 1. Usually only do this on the output layer. It's basically just making it more friendly for probabilities, because you can convert a decimal value between 0 and 1 to probability very, very easily by multiplying by 100. I was talking about it there. There you go, convert scores probabilities. So, what we built previously, I'll just make us comment. This is a neural network yet. This is a linear model. It's only got one layer. To make it a neural network, we need another layer. There's one in the middle. We don't see it. It's not on the input, it's not on the output. It's a magical hidden layer. It just exists in fairyland. It's a black box to us at this point. So to add another layer to our neural network is really easy. we add another line of code. We're adding 128 neurons in this case, with the radio activation I mentioned before, in between our input and our output. And it's still dense, so every single one of those neurons is connected to every single input on both and every single output on both sides. FYI, there are other model types outside of dense, but for beginners, it's very easy just to use dense. Don't worry about it too much unless you wanted to do further reading, which we have resources for at the end. So, and let's talk about the activation. I've got ahead of myself. There we go. So, second neural network from a neural network to a deep neural network, we just add another line. You can add as many layers as you want. Be aware that every layer you add is adding another 128 neurons, and each neuron has 784 connections. So you're very rapidly going to rack up literally thousands of variables, thousands of weights that can be adjusted to make your network more accurate. And your portable laptop might not like that so much. So you go ham, but don't let me feel your web page crashes. So we're actually going to just actually play around with this now. So, always my mouse. There we go. So first thing we're doing is we're going to pre-process the data. So basically what we're doing is we're scaling the data from 20 to 255, which is a pixel value in terms of, when you got a grayscale image, 0 is white, 255 is black, and all the grays are in between. And we're just going to convert that to a value between 0 and 1. We're outputting 0 and 1 probabilities, makes it a little nicer for you want to intake the same thing it's going to output. And it also means it won't be likely to be biased on a high value, so it won't recognize high values as focus more on them than the low values. We want it to interpret both. So we actually get that image that you guys just saw in my slides here. We just run this. We'll plot the first 25 images of the data set. There you go. We're going to scroll through. We can build our neural network. This is just a single layer. I don't know how many you guys have got neural networks, but you're welcome to add more or less if you'd like to. We compile it, so it's really easy. There's lots of flavor text explaining everything in more detail than I have. If you want to read it, please do, be my guest. So we compiled the model, and now we're going to train the model. So here we go. So we just run that. It's going to start training. We should very briefly mention what an epoch is. So we had 60,000 training images. One epoch means the network has trained on all 60,000 images once. 2 means it's gone over all the images twice. So we can train on the same data many, many times. There is a bit of a risk to that, which we'll get to in a moment. Oh, that's not doing it. There we go. So we can see as it's training, the accuracy is slowly increasing. So we've gone from, what is that, 59% accuracy up to 92 already. So we're getting 92% accuracy of recognizing handwritten digits, which is pretty good. Now, if you're having any problems with this model, by the way, just look around some of the DSC shit. Heroes in the back, and probably give you a hand. Sorry for pulling you out. But yeah, so our model finished on 93% accuracy, which is pretty good. We can actually do a quick prediction of a model. We can run a quick test with our separate data. Yeah, and we can see what, there we go. So it ended up on 92. Now, this is a little bit of a different data. You can see it's, was that slightly less? No big deal in this case. If you overtrain a model, or also called overfitting, basically means you have hundreds of epochs. You train on the same, just a small data set, literally hundreds, even thousands of times. And what happens is you start to overfit your model. So your model goes from recognizing the general shape of a 3 to recognizing this little gray pixel at the bottom means it's a 3 because I've seen that 1,000 times this data set I've just trained on. So this little pixel being a value of 0.1 means the image is a 3, I don't need to look at the rest of it. That's bad, we don't want that. Because then what happens when you throw a real 3 at it, somebody hasn't seen before goes, what the hell is this? I haven't seen that before. It's an alien, I don't know what that is. And it just freaks out. So having enough data to avoid overfitting the model is very important. And not training too long on the same data is equally important to avoid overfitting. Anyway, so we see we have an overfit here. We've got a perfect thing. If you have a difference of more than 5% between your training data and your test data, you've probably overfit. You can actually see that here in a moment. So, train our model. We built it, we trained it, we evaluated it. Our evaluation metrics in this case was how many characters you can get right when you train it. But what is training? We just wrote some code and it did something, we don't really know what. And we're now making predictions. How do we go from over there to where we are now? It's a bit unfair. So we're going to try and get through that now. So in order to train a model, we use something called an optimizer. There are a lot of optimizers. In this case, we use Adam. It's a very basic optimizer. It's good for beginners. If you like, once again, not going to go to depth all different kinds of optimizers today. If you're interested, please look at the results at the end. We would love to hear about how you get on. And an optimizer, basically what it tries to do is it tries to reduce loss. So loss is a measure of how inaccurate the neural network is. So there's several different measures of loss. So one example is mean squared. So say you have a neural network trying to guess the prediction of, try to make a prediction and guess how expensive a house might sell for. And say it guesses 480,000, the house sells for 500,000. Then it goes, okay, the difference was $20,000. That squared is your loss. And the network tries to minimize that value. In this case, we're using categorical cross entropy. It's quite a phrase. It's quite simple though. It basically means, okay, this is what the network gave us. Oh, I'm not writing anymore. Why not? There we go. This is what the network gave us. We expected it to give us this. We expected all zeros and 1 because that's what it was. So the difference between these two numbers is 0.4. The loss is 0.4. It's a complicated term for something quite straightforward. So the optimizer, when it makes a prediction, say the neural network guesses a 3. You give it an image and it goes, that's a 3, I'm certain, very sure. And say it's a 7, you bang, bad. We don't agree with that, that's bad, it's wrong. And the neural goes, oh, okay, I didn't like getting told that I was wrong. So it goes back and it goes to its often tens of thousands of weights, depending on how many layers you add, and it adjusts them those values. And the maths of how it does this is extremely complicated. And to be honest, I don't understand it myself. If you're very good at mathematics, you can probably pick it up. It's beyond me. Reza will probably have a better idea than I do, unfortunately. So it adjusts some of these weights by an amount. And then it puts another image, which is something, now we try an image with, say, a 4, and it guesses correctly, it's 4. It goes, oh, that's good. So it adjusts those weights more, say it changes from 0.1 to 0.2, and now changes to 0.3. But then it gets another image and it gets it wrong. Then it goes backwards. It goes, oh, the adjustments I just made must have been wrong. So it goes back and effectively fine-tunes all the weights in the entire algorithm to the point where it gets the least amount of images wrong. It's a very simplified explanation, but it's technically accurate. We are in a beginning talk here. So there is a problem with this though, which I'll mention very briefly, in that if you notice, if you run your training multiple times, you might get different accuracies after 10 epochs, even though it's done the same thing. And that's because the weights are initialized randomly. And when we've got a loss function, oh, thank you. When we've got a loss function, say, let's draw a better line now, I can do better than that. So we've got like something like that, right? If our random weights put us here, we're going to end up in this value here as our least loss possible. Even though if we went the other way, we could have found a much better value. That's because it doesn't know better. If it's on a slope, it just goes downhill, as over here. It just goes downhill. It doesn't matter if over here there's a much deeper pit. It just goes, okay, that's uphill, that's bad. I don't like being wrong. We're going to stay right where I am. I'm going to get as good as I can in my little valley. Now, it's a little more complicated than that, because when you're dealing with this here shows 2 dimensions. You have 3 variables, you've got 3 dimensions. When you're dealing with 11,000 variables, I'm not sure quite how you graph that. It's a bit hard to visualize, but effectively you get stuck in a valley. So if you run it multiple times, you can often get a slightly better prediction or a slightly worse prediction. That's just explaining where that comes from very quickly. Over that, talked about the epochs already. We can actually see this graph here is really lovely. Reza showed me this, is awesome. So we can see as the network is training, these are the bottom guys, the amount of epochs it's gone through. As it's training, we're seeing the validation, the loss is decreasing, so it's getting more accurate, which is the blue line. So it gets more and more accurate. But then our validation data, which is data it hasn't trained on, so unique data it hasn't seen before, goes with it for a point, but then we start to overfit, and then we can see we actually get more inaccurate. Even though the blue line says we're getting more accurate, we're training more, we've done 1,000 epochs, the orange line says actually, mate, you overfit, you're doing worse now. So that's just a lovely little graph showing what happens if you overtrain and overfit your models. Cool. Now we get to generate some predictions. Very exciting. Let's pull this back up. So we evaluated the accuracy. We can make some base predictions, so we'll just run that there, make some predictions, stores in the variable. We can print the predictions. Looks like gibberish. If you notice, there's 10 values there, 1 for each character. We notice one of them is a lot bigger than the rest, which is this one here, which says it's 96% sure that, sorry, 99.6% sure that this number is a 7. And we can actually check what it is, which look at the predictions. It's a 7, they got it right. Obviously, it's got some small confidences. It might be this, might be a 3, not, but it's very, very sure it's a 7. Now, that's actually the end of our basic tutorial for machine learning. You've done the hello world now, and like a hello world, it leaves you wanting more. So please feel free to scroll through the rest of this in your own time. There is a lot of information here. There's a lot more examples. There's a lot more tutorials you work through. It's all very well documented. You can learn a lot from going through this. There's also more resources which you can look at. We won't be coming back to this again. So we generate some predictions, but finally, we actually need to talk about how, coming back to the start again, how do people interact with AI? Because there's a phenomenon been emerging recently where people are on one side of the extreme and one end of the extreme. Either they completely trust the AI, they completely trust that Google Maps is driving them where they need to be 100% of the time, it's perfectly accurate, or they have no trust and they will never use Google Maps because it's always wrong and it's a filthy garbage piece of technology that I hate. So we want to avoid both of those extremes. They're bad. As programmers, we don't like that. We want people to be, okay, we like this recommendation, we trust it, we think it's good, but we're going to sanity check ourselves. So if you're driving a car and Google Maps tells you to go off the side of the bridge, you don't drive into the water. Which, if you look it up, people do that, by the way. There are pictures online of cars in water from people following the GPS blindly into water. It's, yeah, I don't know, man. Okay, so we need to learn about how we make users of our neural networks and of our technology and the systems that we build feel like they know what's going on, they can interpret the results with confidence and have a good idea of what they're actually looking at. And even more importantly, a good idea of that they know what they're looking at is correct or incorrect. So when we go to trust spectrum, we want calibrated trust. Too much trust, they're underwater. No trust, they don't use our app and we get out of a job. So there's three questions we've got to ask ourselves when we're calibrating trust. So firstly, what are the stakes of our app? If we're writing an app that recommends you restaurants nearby or the next track to listen to out of 1,000 you hit that day, stakes are pretty low. Not a big deal. If we get it wrong, whatever. When you're making a recommendation of, okay, this neural needs to try and figure out if someone's got cancer or something else, or do they need to hospital right now because they wait a few days to get an appointment, suddenly the stakes are a lot higher. We're talking life and death. Obviously, the two extremes, but there's a giant range in the middle. So figuring out stakes is important to figure out where, like, how careful you need to be, how much you need to be. Do you need to limit who can use your model? Do you need to provide more warnings? Do you need to do all sorts of stuff? It provides that level of first sanity check how important your model really is in the world. A handwritten digital model, not really that important. So the question is, do we have system data that's going to impact the trust of our users in the model we're developing? So let's say we're writing a competing music app to recommend music to people. Let's call it, I don't know, Bluetooth. Totally not ripping off anything that might already exist. Do we have music data for users who listen to death metal? Do we have data on what they like to listen to, what they might like to listen to instead? Because if we don't, users of our Bluetooth app, when the users who listen to death metal are not going to get good recommendations. They're going to get poor recommendations. They're going to lose faith in the recommendation of our app. Or worse, pop listeners. We don't have data for them. They listen to pop. They're going to get recommended country music. We need to make sure we have data for all of the users of our application to ensure we don't have a lack of data somewhere that's going to impact the recommendations we can make. If we've got, say we do our handwritten neural network there, recognizing handwritten digits. If we only train on digits 0 to 8 and throw a 9 in it, it's not going to know what to do. It's never seen that before. We need to make sure we train on the data that is relevant. All right. So the final thing is user knowledge. So back to one of the previous examples, maybe making an app that helps doctors make recommendations for patients, right? So only a doctor can use it. They have to pay a very large licensing fee. They enter the patient's symptoms and it gives them a potential, okay, these are some of the diseases they may have, this is what they may be ill with. The doctor is a very knowledgeable person. They can go, oh, okay, that person's bleeding from their leg. I'm pretty sure they don't have the cold. They can go, okay, that's clearly a wrong thing. That's clearly a wrong recommendation. I can see that because they know, they have knowledge of the situation. But if you're writing something like WebMD, suddenly you've got Jeremy's mum typing in her son's symptoms frantically at 3 in the morning and it's telling her that her son's got cancer. That's not so helpful because the users is not, they don't know that that's actually bullcrap. They just think, oh, panic mode, I've got to get to the hospital right now because I don't know any better. So the knowledge of our users in the situation and the app we're designing for is important to consider. If we're designing an app that makes medical recommendations, maybe it is a good idea for us to limit the scope of our app to only medical professionals. So let's actually get towards the end of our talk now. Turn to your partner. We do have one of these in here, I'm sorry. But talk about a situation where you've had a recommendation occur to you from a neural network. So it might be a song on Spotify. It might be when your driving app, your GPS, popped up really quickly and said you need to leave in 5 minutes for your appointment that you swear you hadn't told it about. It might be the Netflix show you got recommended. Talk about an example. So much. Thank you. Bye now. All right. So something there's a lot of decent discussion. I actually had a very one of my mates in the front row. He's been having some health issues recently, and his personalized ads on Google have been recommending him health insurance and funeral services. So that might not be the best example of a creepy thing which has gone a bit too far, but you know how these things go sometimes. But anyway, that's actually the end of our talk. I hope you enjoyed it. We do have a couple of plugs here. So devs who recommended this event is actually giving their own machine learning event on Friday, so we highly encourage you to go check that out. We'd also like to make a shout out to the International Women's Day people who actually put together this presentation, which I've modified for today. We're very thankful to them allowing us to use their content. If you'd like to learn more, here are some quick links. Don't worry about copying them down really fast. This presentation, the recording and the slides will be up on our Facebook event after we finish, probably in a few days. If you want some more stuff on explainability, basically how to calibrate users' trust, Google has written a lovely big document, huge website with a lot of information about how they calibrate users' trust. And I'd definitely recommend giving it a look. Thank you very much for watching. All right, if you've got any questions, feel free. Man, what? No, I saw it. Yeah.
You're a Google person. Why were you using Firefox?
I'm a Google person, but I do like to keep my days to myself. All right, yep.
You know how the weights biases are randomly initialized?
Yep.
Is that like really random or in a range of numbers? Or?
As far as I'm concerned, it's pretty random.
They are random. There are some strategies that we can use, but pretty much the random. We can also use transfer learning. That means we use a model that is trained. That means the weights are already adjusted to another problem onto another problem. But one of the issues that we have is about this randomness of initial weights. If your training epochs are not adjusted properly, for example, it's only, let's say, 5 or 10, it doesn't give the network or the optimization algorithm enough opportunity to basically get to that minimum error rate that it requires.
Oh, okay.